you have a big night last night, or?
No, not that guy.
Oh, really? Is he a bit?
He's not coming. Things are good for you. Wouldn't want him here 'cause he's still drunk.
Yeah, rolling in the aisles.
No, and some of them just had to be restarted. Okay. But yeah, I guess he's working on it. Next up, we have Nikolai Freiberg, and he's going to be talking about multiple stressors and their impacts in rivers.
Okay, good morning, everyone. This is going to be a long journey on the runway before a very short takeoff. Before I introduce this subject, we need to divide it up into two things. First of all, we have some issues assessing hydromorphology. I will come into that word later on. And then we have the multiple stress issue. Okay, so hydromorphology was a word that was invented by the Water Framework Directive. You don't find any records of it previously, but it's all about the physical degradation of river ecosystems. It will also apply to lakes, but it's primarily important in relation to rivers. So it's what we would know as geomorphology earlier on, basically. But it's a key component of the river environment. Many rivers across Europe has been physically degraded over time, and it's a real sort of conceived as or perceived as a big issue. So just to make this really applied, if you look into the real world, and you see this is an example from my old home country, Denmark, where you have these river basin management plans, and for this area, which is a fairly large chunk of the island of Furen, home of Hans Christian Andersen, the majority of rivers are not fulfilling their ecological potential due to hydromorphology. So it's quite a large-scale issue, and it's quite important for society to be able to detect and to do mitigation measures regarding to this. And there's some real issues with doing this. Another thing is that we have quite a lot of emphasis on restoration. River restoration has by far been the most prominent type of restoration when we go back the past 3 decades. And the whole idea is that you recreate these geomorphic or hydromorphological conditions, you improve, you make the rivers a better place to live, again for the biota. And also here we need to understand the link between the biota and hydromorphology. And there's a lot of really interesting examples about this. We have this great love of stones or wood, stones in particular. This is again from Denmark, lowland river, full of stones that were collected in Norway and put into a lowland sandy river. I think there's no heading needed. When you see a lowland sandy stream filled up with stones, you can understand that the whole concept of linking hydromorphology with biota is not really well developed in society, and we should work on this. So this is not a straightforward question. Why is the urban river on the left worse than the natural mountain river on the right? So we should say this is a no-brainer, but it's actually not really. I mean, it's often very, very difficult to sort of separate the two. So why is this the case? So this is why I start with a bit about the issue of measuring hydromorphology before I go into multiple stress. Hydromorphology is measured on a different scale. It's often measured on longer reaches than where we take the biota. And the traditional way of measuring hydromorphology has been very static, so it doesn't really have the dynamic influence of processes, which is probably essential to understand also the interaction with biota. So it's very much recording what's there at a given moment in time and sort of overlooking larger scale processes. On the other hand, we have the biological methods that we're using, and they were solely developed for developing water chemistry or to detect effects of water chemistry, water pollution. And this has led to a very, very generally weak relationship between hydromorphological measures like the River Habitat Survey that are applied in the UK and various biotic measurements. Primarily these studies are all about macroinvertebrates, and I have to say I continue with macroinvertebrates in this talk. Okay, so from another study which I did a number of years back, we have on the y-axis a standard measure of quality, the ASPT metric, which is also based on macroinvertebrate, and here we have a morphological index. So a high ASPT value is good and a low is bad. And the morphological index was made from a lot of measurements of all kind of morphology in small rivers that was not impacted by other types of stress. So 0 is really degraded, so it's complete channel without any natural features, and 1 is as natural as you can get it in this setting. So what we see here is there's quite a nice relationship, but what we also can see is that the slope is not very steep. So even across from complete artificial to as natural as you can get it, it's not really very strong response you get in the ASPT. So something is not really, so it's not really fine-tuned. If we look into two metrics that are developed to detect hydromorphological degradation, the MES index and the life index, the life score that is also used in the UK. And we look into two flow conditions. We have normal flow and we have low flow or drought. And we look at the correlation. So if you get a positive high value, it's good. And if you get a negative low value to -1, it's bad. So you can see these two stressor-specific metrics are actually able to pick up the stress caused by low flows. So you have negative values at low flows, indicating that the macroinvertebrate community is disturbed. The problem is then if we put on other stressor-specific metrics, so you have the ASPT again with general degradation, organic pollution, EPT, which is ephemeropteran, plecopteran, and trichopteran. Same story about general degradation, organic pollution, and the SPEAR index on the far right, which is an indicator of pesticide pollution. They show a very, very similar pattern. So there's no real diagnostic capacity. So they do respond, all of them do respond to hydromorphological change, and a manager or anyone else evaluating these results, only looking at the ones targeting hydromorphology, would say, oh, this is the reason if they don't apply the other metrics. So that's quite a big issue, actually. So in many ways, we are comparing apples with pears, and we need to do something about this. So now multiple stress, it would come. So multiple stress is really a reality, and in river environments where I'm working, it's clearly true. Rivers get their water from a catchment area where across Europe, most catchments, if you get over a certain size, would be full of multiple stressors like urban areas, various types of agriculture, industries, and so forth. So you have all these interactions, and on top of that, you have the physical modification, you have the removal of buffer strips, so you have large erosion problems and so forth. So you really you very rarely have only one stressor. So it makes it difficult to know. So diagnostic capability is really something that would be needed. Also, we know that it interacts. This is from another study. We have the number of taxa, again, macroinvertebrates, and we have simple and complex channel forms, and both of them have very high levels of total phosphorus. And we see that we get, in general, we get more taxa in the complex channels compared to the simple channels. So there's a clear interaction between physical environment and chemical pollution in this end eutrophication. The same is true for pesticides. On the y-axis, we have the percentage spear abundance, that's spear taxa, that's taxa sensitive to pesticide pollution. Insecticides, of course, primarily because it's macroinvertebrate. And on the x-axis, we have the toxic units, which is a calculated value of the amount of toxicity from a water sample of various cyanochemicals. In this case, it's all pesticides. And if you have a high value, so you go up to -2, there's a lot of there's high toxicity. So we should have a negative relationship, and we do have a negative relationship. The red one is from homogeneous reaches, and the black one is from physical heterogeneous reaches. But we can see for exactly the same amount of impact from or toxicity derived from pesticides, we have a different response. So the conditions are always better in a good physical environment compared to the poor physical environment. So there's a clear type of interaction. So either, the metric response to the physical environment, or the animals are less susceptible to pesticides when they are in a better physical environment. This is not clear. We always thought for when you had organic pollution, that you've seen the same relationship, and there it's sort of intuitive that if you have slow-flowing water, you will have the risk of getting less oxygen will be higher. But for pesticides, this is not straightforward. Actually, you would expect that the exposure would be higher in the high-flowing areas, so because of lower diffusion gradients. So this actually implies that probably this is something in the metric that we showed before that is that is not really fine-tuned. Okay, so we need to think. I don't know if we really have thought, but I'll give some insights to the ideas. So what we did is that we took a very, very big data set, and this is quite preliminary analysis that was collected in an EU project, the STAR project. So we have 226 stream sites across Central and Northern Europe, all kick sampled at the same time, same methods. And they were actually selected, so they went across various stressor gradient in theory. So there shouldn't be that much of an overlap. There shouldn't really be that many multiple stress sites in this data set, although of course this was all a fantasy. But anyhow, it's probably one of the better data sets, and it's quite sort of it's very high quality in identification and so forth. So we're wondering if there was a link between habitat biotope diversity and macroinvertebrate diversity in this data set. The question that basically has been we haven't had much support from in previous studies. And then we wanted to look at traits. Traits are directly linked up to the local habitat filters and should be much stronger than identity-based taxonomy in detecting the impacts of hydromorphology. So we were trying to do this as a first step. Okay, so we used 20 traits with 107 different trait modalities based on information that are published out there. There's a great European trait database for macroinvertebrates, and there's a very good American one. So it's really easy accessible, and this is by no means a new idea. There's been quite a lot of work with traits in the past, but we're still sort of missing we're still waiting to see the real impact of it. Okay, so the analysis was, we used a very primitive measure of substrate diversity. The first test was to look at if there was a link between nutrients primarily, or eutrophication, and substrate diversity indicators. So we luckily found only quite weak relationships. So we don't really have to consider multiple stress as such in this. I mean, they're sort of fairly pure. Where you have a poor substrate is not necessarily also where you have the highest amount of eutrophication or other types of pollutants. So we tested the diversity against the substrate identity-based indicators of diversity and a lot of different traits. So this is very woolly because I just took it because it's not entertaining at all. But you have the number of mineral substrates, and you can see we would use various diversity metrics on that one, and then the number of taxa and the same type on the biota, and we find nothing out of these 32. We find one weak relationship. So it's very much sort of proved what we already found, that identity-based is not really linked up. I mean, it's quite a shallow analysis, this one. So, but you have to take my word for it. I'm sure even if we did a better job, it would show the same. Okay, so this one is a wonderful slide, and I'm soon to be finished. But actually what we see here is that we saw quite a lot of traits and trait modalities that did respond quite consistently to changes in the physical environment. And some of them are intuitively sort of meaningful, and like organism size, you would guess would be there. You also have the preference for living in slow flow. So what we see here on the organism size is that you have a negative relationship. So with increasing diversity, you will have less small organisms. So when you have a not very diverse physical environment, you'll have a lot of small individuals, and so forth. I won't go into detail about this, but just saying that there was some clear pickup. What we could see was that it was mainly the organic substrate. So we divided into inorganic and organic substrates. Organic would be roots, wood, etc., and inorganic would be gravel, stones, cobbles, whatever. And interestingly enough, the strongest correlation was to the organic. And again, if we go back to the restoration, where you are so focused on, in parts of Europe, restoring the physical environment and not really restoring the biological parts of the hydromorphology, sort of the woods, etc., it's probably not a good thing. We should consider it more. Okay, so the conclusion is that, I mean, I think the traits actually showed promise. Some of them are meaningful. You do understand why they respond to hydromorphology. But again, it's a very sort of preliminary test. And then, as I said, the organic substrates, such as wood, leaf litter, etc., was more clearly linked to the expression of traits than inorganic substrates, which might be something you could use in the context of restoration. But of course, now the next step is to try these traits out in the multiple stress data set, where you have parallel gradients of eutrophication and hydromorphology, because this is where we can see if this is actually able to disentangle the effect of hydromorphology and be a diagnostic tool in the future. Okay, thank you very much.
We've got time for one quick question. Okay, next up we have Frank Burden talking about the impacts of multiple stressors on stream ecosystems.
So I just put next.
It should just come up.
Yeah, great. All right, so this morning I'm going to talk about the holy grail of multiple stress research, which is wastewater impacts in freshwater ecosystems. This is work I've been doing at Auditorium in Switzerland as a part of a large internal project called Eco Impact, and I've been postdocing there. So there's a global biodiversity crisis, and it was really nicely highlighted in this paper by Charles Vorismarty and others in Nature, where they showed in freshwater or river ecosystems that there's a high level of biodiversity threat in certain parts of the world. And unsurprisingly, a lot of these parts of the world were places where there are high human population densities. So this suggests, obviously, that humans are having unsurprisingly, large impacts on the environment with disproportionate contribution to the biodiversity threat with freshwater organisms. And a major sort of component, I guess, of this threat is through pollution, both through diffuse pollution associated with agricultural land uses, but also point source pollution, which is mainly driven by municipal wastewater that comes from our use of water, basically, and our waste. So obviously that biodiversity threat is, links to ecosystem functioning. And one major ecosystem function in stream and river ecosystems is organic matter processing. And just to run you through some general sort of ideas about that, in streams, particularly headwater streams, you quite often have detrital inputs from the terrestrial environment as the main source of energy. And so the way the system processes this organic or this energy source coming from the terrestrial environment is a really important ecosystem function. And so it's quite often used as a biomonitoring tool because it's interactive, it integrates different biotic responses. And so it's a major use for managers as well as also of scientific interest. And probably the most notable study using this sort of approach, measuring detrital processing, was the study by it was the RIV Function project, which was a large sort of EU project. And the most notable publication was this Woodward et al. Paper in Science, which described basically patterns of litter decomposition in a number of sites across Europe in a large sort of geographical area. And they found this interesting pattern where you have this sort of hump-shaped response along nutrient gradients of phosphorus and dissolved inorganic nitrogen, that you get this sort of optimum of nutrient enrichment that basically gives you the fastest ecosystem processing rates. And just to talk you through what might be happening with that response, I've put this into a simple schematic. So here we have ecosystem functioning. This will be litter breakdown and our nutrient gradient. So the idea here is that as we add nutrients, we actually get some sort of subsidy effect. And that probably helps contribute to large or shredder and also decomposers like fungi, so that you get maximum breakdown rates. But as we go further along this gradient, we start to see antagonistic effects of other stresses that are co-occurring with those human impacts. And these could be things like fine sediment and hydromorphological degradation, but also the inputs of pesticides and other things associated with sort of human land uses. And one of the questions that I'm sort of going to try and address today is, is this effect real? And also, is it priming the system for the maximum impact of a local disturbance at this sort of nutrient optimum? And so to put that in very general terms, the question is the effect size of a disturbance context dependent? Just to talk you through some more specifics about organic matter processing, you have your litter inputs, which are donor controlled from the terrestrial environment, the riparian environment. You have microbial decomposers, which are very important, and sort of conditioning this very sort of raw material and facilitating then the activity of invertebrate detritivores. And you'll see this is an amphipod. And I'm going to be talking mainly about gammarid amphipods today because they're a sort of keystone shredder in a lot of European streams. And so the disturbance I'm talking about today also, as I've alluded to, is wastewater pollution. And when I said it's the holy grail of multiple stress, I'm not lying because there's a lot of stresses in wastewater. One of the main ones is these what we call micropollutants, but these are things like pharmaceuticals and pesticides. They have different modes of action. And so what that means is if you have insecticide, it's obviously more likely to be acting on your invertebrates, whereas you might have fungicides as well, which could have negative effects on these decomposers. So there's potentially multiple effects nested within that stressor group. But you, of course, also have other things in the wastewater, and one is you're getting nutrient inputs. You're also getting some microbial inputs from the wastewater, which could be quite important. And also often there's localized stream warming, so you're actually warming the system as well. And so here I've sort of put in positive effects, net effects on decomposers, but more than likely negative effects on our invertebrates. And so what that means is that we see less invertebrate-mediated shredding, but potentially we have positive effects on our microbial decomposers, and this may have, may actually dampen some of these negative effects that we're seeing on the invertebrates. Okay. So to study this, we have taken 20 streams across the Swiss plateau. We have 3 sampling locations on each stream. So we have 2 upstream reference sites and 1 downstream impacted site. So here we have a wastewater input, and water's obviously flowing downstream. And so this is our disturbed, perturbed site, and we have 2 upstream controls. And what we've done is basically used the same method, what's described here in the Advances in Ecological Research paper, but that's the same methods that we used in the Woodward et al. Paper in Science, the river function study. So that's basically, we have 2 litter types, oak and alder, and we use fine and coarse mesh litter bags. Today I'm only going to be talking about alder responses. Okay, so here's some results. This is basically our nutrient gradient here, dissolved inorganic nitrogen, and this is our breakdown rates, and these are corrected for temperature, so these are expressed in degree days. What we have here in blue is the total breakdown rates, red is the invertebrate-mediated component, and then in the green here we have microbial-mediated decomposition. And you can see more or less this is not showing any response, and that is partly due, there's a lot more explained basically by temperature than any of the other potential explanatory factors. But what we do see in the solid line is this pattern, and these are from the upstream sites, that we see the same sort of hump-shaped response, that we're getting some sort of nutrient optima, and then it's falling off as we progress along that nutrient gradient. But interestingly, what we see also is that the downstream sites, which are impacted by wastewater, that this sort of hump-shaped response is greatly dampened or suppressed. And so the question is, do we see the greatest impact of wastewater disturbance at this sort of nutrient optimum? So here I've tried to measure that effect size using Hedges G and plotted that along the nutrient gradient here. And so this is basically negative effects, and the larger they are, the stronger the effect of that wastewater at the downstream sites. And here we have the 95% confidence interval and the actual lowest smoothed effect size. So there's a lot of scatter here. It's not totally clear, but we do see some sort of peak maybe at that sort of nutrient optimum. And going a little bit further, we also start to think, okay, what's mediating that? And looking at the gammarid densities at the upstream sites, we see that the effect size is, or shows at least at some sites, some correlation with the magnitude of impact. So what that's saying is that nutrients are facilitating large densities of gammarids, and where we have large densities of gammarids, the system is more sensitive to that input of wastewater. But there are outliers, so there are other things happening. Some sites we don't see gammarids upstream, so we don't get the same response. Okay, so I'm going to try and walk you through a structural equation model now. This is quite complex, but they're a very useful way for describing multiple interactions in the environment and trying to understand what processes are contributing to our responses. So we're going to start off with the proportion of wastewater or in the river, basically. And we can see that this contributes a number of different stresses to the river ecosystem. So we have What we're measuring in here is toxic units, so this is a sort of risk factor associated with toxic elements in the water. And so we have the non-insecticide component. We have insecticides, so these are the sort of common pesticides that have been applied to agricultural lands and also used in the household. And then we have our nutrient component, so this is phosphorus, measured as SRP, which is soluble reactive phosphorus, and also nitrogen, again, is dissolved in organic nitrogen. And so what we're seeing is wastewater is contributing a lot of different stresses to the system. But what we also have is upstream land use effects. So here we have proportion of arable cropping in the upstream catchment, and we can see that at least for two of the stresses, we're seeing increased nitrogen levels, and also we're getting insecticides associated with those agricultural land uses entering the river environment as well. So we have two what we would consider pressures here, contributing a number of different stresses to the system. And these stresses obviously have potentially different effects. So here we're looking at gammara densities in the leaf packs again, and we can show using this, this model that we actually do have positive effects of the nutrients on the densities of those consumers, but we also can show that here we have negative effects. And so these are path coefficients with one standard deviation, and the star there indicates some significant relationship. And also you'll see here we have R-square values. This is a marginal R-squared value because this is a piecewise SEM which includes random effects. And so this is basically a marginal goodness of fit. So we can see for some of the stresses is not explained well, but others we're getting very good explanatory power basically with R-squares, so they're relatively high. So this is quite an important result. And so what we know now is that gammara density is a strong determinant of litter breakdown. We can also see that there's other factors like phosphorus having positive influences on that process, so that's probably mediated through positive responses by maybe the microbial decomposers. But we also have a negative direct effect of wastewater, and that's probably because there's other shredders than gammarids contributing to breakdown, and so that the wastewater is also having negative impacts on them. Right, so just to run through a quick summary, we saw a subsidy stress gradient along that nutrient gradient, which is very similar to the Woodward et al. Paper. There was some evidence for the magnitude of the wastewater disturbance, so that effect size being context dependent along that nutrient gradient. Importantly, we can show, and this is similar to other studies that have been published, that pesticides have really strong effects on gammarids, which then obviously affects ecosystem functioning. We can trace that back to different sources as arable cropping and wastewater discharges. And I guess the sort of main take-home message is that we have multiple stresses in the environments, but we also have the fact that these combined can be also, the effects can be environmentally contingent. And so here I've shown how this nutrient gradient may be priming the system for the greatest fall at intermediate levels. And so, using things like structural equation models is a really useful way for starting to put a lot of information into a more causal network type approach. And with that, I don't have any acknowledgements because I think most of the people that contributed to the study are listed as co-authors in the program. So thank you.
Frank, we don't have any time for questions, but I'm sure Frank will answer any in the break if anyone has any questions. Okay, next up we have TAS Pro, talking about the combined effects of multiple stressors and how they can vary their interactive effects.
Okay, good morning everybody. It's very nice to be here. I'm going to be presenting some work that was primarily done by my PhD student Paul Brooks, but in collaboration with two postdocs, Mark Brown and Evan Lyons, and another colleague, Lisandra Benedetti-Cecchi from Pisa. So, as we've heard, human activities are imposing a wide range of different kinds of pressures which give rise to stressors in the environment, in this case the marine environment. And I think it's useful to distinguish between the kinds of pressures that are local to regional and are potentially controlled in principle by by our kind of governance and environmental management, such as agricultural and urban runoff, construction, and tourism and recreation kinds of activities. And also between those kind of changes that are being driven at a larger scale and over longer time frames and that are essentially with us for the coming few decades, no matter what we do in the short term, so that we're in a position where we can only adapt to and mitigate against those effects and consider their influence in the context of the local and regional stressors. So for a lot of these kinds of the stresses associated with these kinds of pressures, we have got some understanding for a range of important habitats and ecosystems. What's less well developed, though, is which is the reason we're here, is our understanding of how those different stresses combine to influence ecosystems. And the pressure to improve that understanding is particularly great in an environmental management context in Europe, because the European Commission is prepared to take member states to court if they fail to take account of the cumulative effects of multiple stresses in certain contexts. I appreciate that this may be less of a concern in the UK in the coming years, but nevertheless, we should be concerned about it. So, any combination of stresses, two stresses, A and B, which have a measurable effect in the system, broadly speaking, and there are nuances around this that we could explore, but broadly speaking, can either have sort of straightforward additive effects in which the overall effect is effectively the equivalent of the sum of the parts, or there can be interactive effects in which the influence of one stressor modifies the action of the other, so that the combined effect is either less than the sum of the parts, antagonistic, or more than the sum of the parts, synergistic. And based on knowledge that we may already have of individual effects of stressors, we would in principle be able to anticipate the impacts of combinations of stressors if they were combining in an additive way. But it's much more challenging if there are ecological surprises, ways in which they combine that we are currently unable to anticipate and don't have the evidence to support. So this would be more of a concern in an environmental management context. The evidence of the reviews of the evidence to date suggest that there are more or less equal proportions of outcomes under of these three categories for the combinations of stresses that have been explored so far. So that's the kind of ballpark estimate that we're seeing emerging from this active field. But a lot of that work has been done based on either binary designs like this or something similar to it. So where you either have control conditions in which there are no stressors added, elevated levels of one stressor, elevated levels of the other stressor, or elevated levels of both. And of course, these can shed important insights on the combined effects of multiple stressors. But they don't tell the whole story, and they may not always be a good basis for anticipating effects in the real world. So what we really would ideally be able to deploy would be these kind of response surface designs where we impose multiple levels of each of the stressors and their combinations. Right? So this gives a much better notion of whether those interactive effects are occurring at a range of different levels of those stressors. The effects of those stresses can be manifested at a range of different levels of biological organization, from the intra-individual through to the community and ecosystem level, with the speed of the response maximized at the top, and what you might consider the societal relevance in terms of conservation objectives, ecosystem services and benefits to society, most prominent at the bottom of this hierarchy. So to better understand the consequences of multiple stresses in the environment, it's very useful to take an integrated approach across these levels of organization if we can. And this is also useful for exploring the effectiveness of biomonitoring tools that are quite often based on measurements made at the intra-individual level at predicting consequences at the community and ecosystem level, which is where society is more directly concerned. So in this piece of work, we wanted to address two objectives, essentially. We wanted to test, firstly, whether variation in the concentration of multiple stressors influences their combined effects. And we also wanted to ask whether those effects vary among levels of biological organization, or whether, in fact, they're quite consistent across levels of biological organization, so that we can be comfortable with indicating environmental quality with measures taken at one level and applying them to other levels in that hierarchy. And when you kind of break that kind of response surface design into a sort of more traditional stick diagram to visualize it, so in this case we were interested in the influence of copper, heavy metal, and a common biocide, chlorpyrifos, which finds its way into coastal and estuarine environments as agricultural runoff. When you explore a design with multiple levels of each, it adds up to quite a substantial piece of work. All right, so this is 25 different treatments, 100 different experimental units. And so these kinds of designs have rarely been deployed in the field before. And we were interested in the effects on mussel-dominated assemblages in shallow coastal systems. So the logistical challenges needed to be overcome. And I was very lucky when this research was developing to have two very dynamic members of the research group, so Mark Brown and Paul Brooks, who drove forward this initiative to establish a research facility at Malahide Marina just north of Dublin, which would enable us to manipulate combinations of those stressors over extended periods and deliver them to 100 different experimental plots on the walls of the marina. So this system involved 11 kilometers of piping, a kilometer of electrical cable, a series of pumps and electronic timers, and as I say, delivered the stressors to our experimental plots. So the idea came from Mark, but Mark and Paul worked together in a very effective, although sometimes fractious, partnership. And after 6 weeks of pumping contaminants in small controlled doses into the system to our separate experimental plots, measurements were made at two levels of biological organization, the intra-individual level, looking at accumulation of copper in the tissues of the mussels, and the cellular viability of the mussels using the neutral red assay, which is a widely applied biomonitoring tool. Mark also took the initiative in designing a chamber with the Sydney University Robotics Department to measure ecosystem processes in the field by isolating clumps of mussels and their associated biota and a block of water to be able to look at changes in gas concentrations to measure community respiration and changes in concentrations of a known dose of algal particles to look at clearance rates, which is an important ecosystem service. And in fact, mussels are doing this for us right now just outside this conference centre. They're cleaning up the dock water. They were very prominent in clarifying the dock water in the Albert docks when it was first developed. So I'm going to show the graphs for each of those outcomes on a diagram like this. So at this point, there are no stressors added. As we progress along this axis, there are increasing concentrations of biocide. As we progress along this axis, it's increasing concentrations of copper, and all the points in between are the combined levels of those concentrations. And what you can see in terms of copper accumulation in the tissue is if you track along the biocide axis, there's no increase in the concentration of copper, which is what you'd expect. No copper's been added. But where you track along the copper axis, there's a gradual increase in the concentration of copper in the muscle tissues. But what's striking here is that there is a synergistic effect in combination with biocide, so that the peak copper accumulation in the tissues is not just where high concentrations of copper added, but where there's also intermediate levels of biocide added. If we look at cellular viability, which has its peak under control conditions here, you can see that this is the biomonitoring tool. It reduces as you add single stressors, and this is well established that this is an effective indicator of responses to single stressors. But again, if you look at the response surface, you can see that there is actually an antagonistic effect, so that the influence of copper at high concentrations, for instance, is being diminished is being counteracted by high concentrations of biocide in the water. So the combined effect of high concentrations of copper, intermediate concentrations of biocide would give you a measure of cellular viability that's not so different from control conditions. So they're masking each other's effects there. If we look at whether this relates to the ecosystem level effects, in terms of clearance rates, we've got a good correspondence in relation to biocide with a gradual decline or a decline in clearance rate with increasing concentration of biocide. In copper, in the case of copper, it's a parabolic relationship. But again, we have an interactive effect here at a synergistic effect where clearance is reduced to zero with high concentrations of copper and intermediate concentrations of biocide. So it's a particularly bad combination. In terms of community respiration, there's comparatively little effect of adding copper on community respiration, but in relation to biocide, there's a substantial peak at intermediate levels of biocide, so a high response to intermediate levels of biocide, but there's an antagonistic interaction with copper. So if you then progress along the copper axis, there's a counteracting of that influence on community respiration. So, and these two ecosystem level responses then in response to multiple stresses are not tracking what you would expect from the biomonitoring tool. And none of these effects would have been detected had we focused just on the four corners of these surfaces. So in conclusion, we found that ecosystem level responses were not always predictable from intracellular responses. Although the biomarkers were very effective in indicating responses to single stressors, multiple stressors reduced their effectiveness in indicating stress, and also we would say that they don't always indicate effectively impacts at higher levels of biological organization. We also found that combined effects of stresses varied at different concentrations, which means that looking forward, these kind of interactive non-additive effects of multiple stresses may be more complex and more common than we would have expected based on simple binary designs. So they're more often cropping up than would have been revealed by those binary designs. So I would say that work of this kind is needed to help improve that level of understanding if we are to manage the wide range of human activities in a given area, to look for optimal combinations to support conservation objectives and the provision of services and benefits to society. So thanks very much, and thanks to the funding, especially to the very patient staff at Malahide Marina, and to a large number of people who helped out at all hours of the day and night with the fieldwork. Thank you.
Anyone got any questions?
That's a good question. So there weren't dramatic compositional shifts in that 6-week period. So I mean, the most powerful drivers of those community respiration results would have been the mussels themselves. They were kind of 60 to 70% of the biomass in the system. So I think there wouldn't have been a substantial compositional shift, and certainly the mussels were still in situ.
Okay, thank you.
Thanks.
Next up, we have Mark Trimmer talking about how methane emissions. We have Hong Din talking about the combined impacts of warming and contaminants impacts on birth rates.
Okay, good morning, and it's my great honor to be here to presenting about my research topic in last 6 years, 7 years. So basically about the combined effect of global warming and contaminants, not only simultaneously, but also in sequentially. So there already quite some talk about global warming during the meeting here in Liverpool now, and there's no doubt about global warming. And my main focus with global warming here, you will see about how the increase in mean temperature effect on aquatic organisms, and some experiment about the extreme temperatures. And also another important stressor for aquatic organisms is pollutants like pesticides, heavy metals, and other toxic compounds. And it is expected that both stressors will become more severe in the near futures, and the interactive effect of global warming and contaminant might result in ecological surprises. So, starting about the very influential reviews of noise around 2009 raised the concern about the interactive effect of global warming and contaminants. And later in 2012, a special session in environmental toxicology and chemistries calling for research about interactive effect of global warming and contaminants, but so far it's not enough. And in my research, I not only focus on the direct interaction of global warming and contaminants, but also the delay in interactive between these two stressors. So, first of all, under global warming, there's some adaptive response of global warming, of organisms to global warming, just thinking that if this is global warming, what should animals do? They can do nothing, just be there, enjoying the warmth. And to be so, they have to develop a thermal adaptations, but my argument will be if they invest more for something, then they will have less energy for something else. Then how they will deal with the contaminants. And if it's continue to be warmer to over the tipping point, they may die unhappily. Or they might choose to disperse where. Many studies show that they move to higher latitude or higher altitudes. Then to migrations, they have to invest more for dispersal threats, like longer lengths of wings. And also the same question, if they invest more for something, then they may have less energy for something else. And about the genetics behind all the the trade-off or different investment. So how to test the role of thermal adaptations of animals under global warming? The direct methods just expose the animals to many generations to the increasing temperatures. And the indirect methods is called space for time substitutions. I would explain a bit about this. So let's say if now we have one population living at 20 degrees and we want to study how 4-degree increase in temperatures under global warming would affect the animals. The very simple step is just put them at 20 and 24 degrees and see how they perform at two different temperatures. In this way, we call the shock approach because in nature it might take hundreds of years for temperature increase 4 degrees, but in the lab you just put like after a certain period of acclimation, then you do the test. Then at the same time, we found that another population of the same species, they are living in the south and in a lower latitude, and then they are already adapted to higher temperatures. So the difference between the south, the low and the high latitude population, just exactly different between the predicted now and the futures. So what happened in the southern, in the low latitude population now might give some indicator for what might happen in the high latitude population in the future. So this we call the space for time substitution approach. To study this, I have spent 4 years in my PhD working with damselfly species. They are very, very beautiful animals. And with different populations from the southern, the low latitude to the high latitudes, and with different contaminants like heavy metals and pesticides, so to see how they deal with them. And first of all, with zinc, you can see that's at 20 degrees, nothing happened, they all survive. But at 24 degrees, you see the different, at high concentration of zinc, so only the Swedish population, they have the very high mortality. Apparently, if they, but not in the French population. So if they have the thermal adaptation, the Swedish population might have the same level of performance like the French animals. But with chlorophylls, it's a bit not very clear here, but somehow you can see that at high temperature, the French population, they suffering much more from growth reduction to chlorophylls than the high latitude population. It is, well, some explanation might be because of the French population, they have 3 to 4 generations per year, so they develop much faster than the Swedish population. There's only 1 generation per 1 or 2 years. And then they might suffering more. The faster they grow, they might suffering more from contaminants. So, you know that the multiple stressors might occur in the nature not only simultaneously but also sequentially, just randomly in time or space. And we also know that under global warming, the extreme events such as heat waves might be more frequent and with the high intensities, severities. So I would like to know how aquatic animals would deal with the extreme temperatures and also in combination with other stressors like starvation or with the pesticide. So first of all, they was exposed to both heat wave and starvation, and what happens? Well, you can see they decrease the growth rate, but I mean they won't survive. So not lethal at all, even with combination of 2 stressors. But when both stressor is over and then the encounters another stressor like pesticide, here the animal, they have the delayed effects of heat wave and another delayed effect of starvation and the direct effect of pesticide. And what happened, you can see here that half of the population die with all 3 stressors together. So 1 direct effect of pesticide and 2 delayed effect of starvation and heat wave. For the many species under global warming, well, as I already told before, that they choose not to stay, but to migrate to higher latitudes. And to do so, they have to invest more for the dispersal stress. And also, dragonfly and damselfly, they are one of the group that show the very high range expansion under global warming. And I tested with 4 different populations, 2 core populations, they just stay there, and 2 expanding populations in the edge of the species range. So when I exposed them to pesticide chlorophylls, and then I did not see any pesticide effect here. You see there's no difference between pesticide and control at different food levels. But when they become adults, and then I measured the fly muscles, so you see that is the fly muscles decrease in the edge population, and this might result in the consequence for the range expansion in the near futures. About marine animals, what I'm working now. So a couple of years ago, a very interesting reviews about the studies of on the marine animals, and you can see here that most of the study focus on 2 stressor, temperature, acidification, and on temperate animals, and with benthic invertebrates, and with 1 species. And my main interest in now is to study the effect of global warming and contaminants on the species, focusing on the species living in extreme environment like the Arctic or the tropical ecosystem, because the global warming here the temperature might increase beyond the upper thermal threshold of these species, and in combination with oil pollutions. And with corpus species, because they are the key group in the marine ecosystem, and with different temperatures from 2 to 34 degrees from the Arctic ecosystem to subarctic temperatures, or subtropic and to tropical ecosystem. So this is my overview of my current research with different group of and different corpus from polar to tropical ecosystem, and from the life history trait to the physiologists, and at the final phase, I would like to make a prediction for the global map based on the modeling, and with some information about the corpus species in the Arctic that we have done this year. So these are the two true Arctic species, and this species was migrating to the Arctic ecosystem. And this is when the ice melting, and then the cohort, they just migrating up to eat the food, reproduce and have baby and eat food, and then migrating down to the deep over winter, and then the next cycle will come next year. And then this is what we have go to collect the sample on the sea ice. And this is the Arctic station that we have done the experiment. There, this is the species that we test. And some results that you see that the Calanus fimachus, they are North Atlantic distribution and now migrating to the Arctic ecosystem. They deal much better with the higher temperatures. You don't see any difference between the temperatures to 2, 6, and 10 degrees. But with the Calanus glacialis, they are true Arctic species, and you can really see that they increase the mortality at high temperature at own concentration here. So there's various evidence for both direct and delayed interaction of multiple stressors on aquatic ecosystem, and this is very latitude specific. And my main concern is how organisms in extreme environment like polar or tropical ecosystem deal with both two stressors, and this is, I would like to thank a lot of my students, professors, and that's helped me a lot during the lab work so far. Thank you very much.
So no other questions? Yeah.
I have one question with a follow-up question. So what was the duration of your heat wave? And the follow-up question is like, was it a gradual increase, then a plateau of stable increased temperature, and then back? So
For the heat wave experiment,
yes.
the duration for the heat wave experiment was 6 days, and then it's increased from 20 to 24 degrees in one day, and from 24 to 28 in another day, and stay at 28 for 3 days, and then go down to 24 and to 20 degrees.
Okay, so there was
Yeah.
like a 4-degree increase just within a 1 day from when you started and
Yeah.
then you reached the peak and then
Yeah.
I saw another question there. Did someone else put their hand up? Yeah.
Yeah.
Yeah. Yeah.
yes, so I was wondering what your predictions are for the tropics about the stress and
My predict. Could you repeat the question again?
what your predictions are for the tropics, because in the Arctic there's a lot of species that migrate up there, and if there's any movement in the tropics.
That might be more severe considered for the tropical animal, because like now if we are here and then with temperature from 10 with 5 degrees to 15, or even with 10 degrees to 20, we might be happy with that. But at 30 degrees and increase to 34, 36, 37, it's just boiling water.
You will have nothing, not going to feel that much. If you have impact coming from the tropics, they're adapted to these high temperatures. So what will happen when temperatures increase?
It depends on if it go beyond the tipping point, and because in the coastal areas with shallow water, the constitution might be more severe than in the open water. They can migrate up and down.
So you will have no any impact on them.
I hope it would not occur. They may migrate.
Okay. Thanks very much. So our final final talk of the session is Chris Hassel, again talking about the combined impacts of warming, but this time with invasions.
Thanks very much. So apologies if you were expecting Steve Ormerod. I hope I can at least partially fill his rather large shoes. I'm going to be talking about some work that I did with a very talented master's student last year. So I've been working on climate change for a number of years, and recently, well, last few years I've been at Leeds and talking to Alison Dunn a couple of doors down in the corridor. She's really interested in invasive species, so we slammed the two fields together, and I'm going to tell you about some of the early work that's come out of that collaboration. It's just about to come out in Ecologia as well, and it's available as a preprint. If you want to read the paper, I can send it. So Taz Crow set the scene quite nicely for this idea of how we think about synergistic, additive, or antagonistic anthropogenic stresses. Most of us, when we try to talk about threats to biodiversity, we talk about individual stresses, and we try to focus on climate change being the second biggest threat to biodiversity, and we cite Sala or whoever it is. But as we all know, these things very rarely operate in isolation, and actually more of the time there's multiple stresses operating simultaneously, and that can lead to quite complex outcomes when we start to measure response variables. The review that Crane and co did in Ecology Letters a few years ago in marine systems is very really emblematic of how the field is trying to distinguish these synergistic and antagonistic patterns. I know Jay Piggott takes some issue with some of these patterns, but he hasn't produced such a nice plot, so I'm going to stick with Crane for now. But you can see the distribution of the additive, antagonistic, and synergistic interactions between individual stressors and the various other stresses with which they've been studied. So we have reason to expect that, as Taz was saying, that there's going to be a roughly even distribution of additive, antagonistic, and synergistic interactions between these stresses. So it's of interest to try to study them in an experimental way to tease apart what's actually going on at a mechanistic level. So the first stressor, as I said, is going to be climate change. We've talked a lot about IPCC projections and atmospheric temperature, but actually when you look at water temperatures now, we've got sufficient hydrological records going back that we can detect the hallmarks, the signatures of climate change in the water as well. So we're really beyond the need to think about atmospheric temperature as a proxy for water temperature. We have those water temperature data now. And that's true for both the Global Lakes database, where anything red here is warming, and the UK river system, UK river monitoring, where again anything red is warming. And you can see the vast preponderance of warming trends in both types of environment, both lentic and low-tic. The second stressor that I'm going to talk about is this new collaboration with Alison Dunn. So she's been working on biological invasions for a number of years. Here we have Himalayan balsam, this beautiful plant that everyone likes to plant everywhere and is horrifically invasive. And a series of the usual Project Fear style detrimental impacts of biological invasions with a focus on the UK. So global economic loss of around 5% of annual global production, 40% of animal extinctions are attributed to interactions with biological invasions, 20 to 30% of all introduced species cause problems. This idea of ballast water comes into play with a particular system that I'm going to be telling you about. There's a whole lot of shipping that goes around moving vast quantities of propagules of different species. We have an increasing, rising trend for invertebrate and marine fish introductions in Europe, and the cost to the British economy of invasive species is about 1.7 billion in terms of mitigation and preventing the arrival in the first place. So this is a very contemporary and growing issue in biodiversity conservation, with lots of nice or not so nice economic consequences as well. The study system that I'm going to tell you about then is Dichorogammarus villosus. This is the killer shrimp, because amphipod biologists like to give things dramatic names. Dichorogammarus is a Pontocaspian species, so it's found out towards Russia. That environment tends to bring with it a series of adaptations to high temperatures. It's a particularly robust, large, and vigorous species. It's present at a number of sites now, and on the map here, this is 2 Dichorogammarus species. The red is villosus here. It's certainly present at these 2, and there's evidence that it's present at a number of other sites, and to be honest, we're probably at that stage now where it's a lot more widespread. We just haven't looked. So it's probably spreading very quickly. The other species on here is Dichorogammarus hemabaphis, which you can see follows canal networks quite closely. It's a preferred habitat. It's a major threat to Europe, but it's also threatening the Great Lakes as well, so it's not just affecting the UK. And I'll talk about resource processing with it, but actually the interesting thing is that the species tends not to shred. It preferentially predates on other organisms, including our native keystone shredder, which is Gammarus pulex. So this is the species against which we compared it. Gammarus is our control, effectively, for the biological invasion. Gammarus is the thing that you pull out in every pond sample, every river sample. It's a keystone shredder. It can shred sort of half of all resource processing in a lot of streams can be performed by this one species. So it really is a keystone species. So we were interested in looking at these two stresses, the impacts of climate change and biological invasion. And one particular aspect that we were looking at was how you can integrate behavioral responses to temperature change into these kinds of multiple stressor experiments. So going beyond just putting things in a pot and heating them up, we were interested in whether or not the two different species showed different thermal preferences. You would expect so, given the fact that they've come from different landscapes with different thermal histories. And then on top of that, we can ask at which temperature do they perform best. But then we can combine those two questions to see whether or not the species are preferring those temperatures at which they perform optimally. And we can start to scale up to look at projecting some of these laboratory experiments into the field to look at what the emergent properties might be once we incorporate these different life history traits. And finally, once we've got this kind of scaled up model, we can look at whether or not the processes that we're looking at are actually synergistic or antagonistic. So I'm going to talk you through how we did each of these parts of the study. I was talking to Dan when he first came to me to join the lab. I described to him a vision that I'd had. And Dan went off and within days had constructed this thermal gradient experiment, which worked really, really well. So all it is a nice bath at one side and a series of aquarium heaters at the other. And we were able to establish a really nice thermal gradient going from around 5 degrees to about 20 degrees from one end of the equipment to the other. It's got a loop to avoid the positive thigmotaxis. So all these amphipods like to cram into corners. So we tried to provide them with an environment with as few corners as possible. So this is the experiment within which we did the thermal preference work. We had 30 pulex, this is our native, 30 invasive, at each of 3 acclimation temperatures, representing the continuum of temperatures across the gradient. I'm not going to talk about what happened between the acclimation temperatures, because there wasn't any effect. They all preferred the same temperature. And when we look at the amount of time that they're spending in different parts of the apparatus, what we see is they use bits of it at different times, but there's a very definite peak in the middle. So the 3 solid lines here are the native species, 5, 15, 20. You can see there's not much difference between them. And the dotted lines are the invasive. So the natives very much they show a very strong preference for this intermediate temperature. And sometimes the invasive really uses the extremes of the distribution of temperatures as well, and particularly the warmer end. So we have some evidence, and this is statistically significant, that there's a preference for higher temperatures and a broader temperature range in the invasive. So what does this mean in terms of function then? We conducted an experiment replicated across 8 different temperatures, spanning the breadth of our thermal gradient from 5 to 22.5 degrees. Standard photoperiod in the lab, we used sycamore leaves just because they're a very common resource in British streams, British ponds. The design was quite extensive, so we had 10 replicates of size-matched individuals because we were interested in comparing across sizes to control for mass. But we also used additional replicates which made use of the remaining range of the species body size, because Dichorogammarus is about twice the size of Gammarus, so the invasive is about twice the size of the native. The 8 temperature treatments, 2 species treatments, the 2 size treatments, each replicated 10 times gave us 320 replicates in total, and this is what it looks like when it's set up in the incubator. So what did we find? Just to help you with the interpretation of this, the black dots are all the native species, and the open dots, the open symbols, are all the invasive species. And what I'm showing you here is the proportion surviving at the top and the shredding rate at the bottom. Control for standardized temperature, because we did some metabolic theory work as well, which I won't talk about today. So what we see very obviously is that there's a much more rapid decline in survivorship with temperature in the native, whereas the thermophilic invasive species survives much better. Intuitive, but nice to demonstrate that actually these are relatively linear trends. And the same linearity is true present in the shredding rates as well. So just as Taz was saying, rather than sampling at each end of the continuum and assuming or interpolating between them, we've demonstrated that there's no nonlinearity in this particular stressor. So this is much higher shredding rates in the native versus the invasive, perhaps offset by the survival rates, and I'll tell you about how we incorporated those together in a moment. When we compared the thermal preference, that's the time, the activity plot from the first set of results, with their performance, so you can categorize them according to the number of position records at each temperature, we could try to evaluate whether or not these species were preferentially selecting the temperatures at which they perform best. And there's no evidence for this in the native. You have to believe me that there's weak statistical significance for an effect in the invasive. So we seem to see a plateau at this kind of optimum feeding rate where they spend more time at those temperatures where they perform best. This is using a deeming regression that takes into account error in both x and y with some nonlinear curve fitting. So that's of interest, and I don't think that's been shown before that there's a difference between invasive and native in terms of their capacity to preferentially select microhabitats. So this is the graph that sums up all the work that summed up an awful lot of effort on Danny's part. What we did was we built a very simple population model where we assumed that a population of amphipods had 100 individuals in it. We used our 72-hour period during which we incubated the animals with their leaf resource. And then we combined all the outputs from the different variables that we've measured. So we had mass-specific shredding rates. We know the mean mass of each species. So, as I say, about half the mass in Gammarus pulex is about half the mass of the invasive species. But we can also incorporate the survival rate because, of course, any shredding that occurs is going to be done by animals that aren't dead, which actually is surprising how few times that's incorporated into these sorts of measures. And just again to guide you through, what we have is a relatively stable shredding rate across the range of temperatures in Gammarus pulex with quite a lot of variability, because while they're shredding more at higher temperatures, they're dying more as well. So the sum total is that actually that doesn't create any net increase in shredding according to this relatively simple model. However, Dicera Gammarus, as you increase the temperature, because it's dying less while it doesn't shred as much, there is a temperature increase, a thermal increase in shredding rate. And eventually what you see is that at the highest temperatures, it's shredding at the same rate as Gammarus pulex. So this is an example where, despite the fact that we've got an invasive that we know is damaging, actually, as climate change increases, potentially that biological invasion is going to offset the loss of our native species. So just to sum that up then, the invasive but not the native species seems to be able to thermoregulate to occupy those temperatures at which it performs best. All things being equal, and this is the important part of multiple stresses work, biological invasion, therefore the replacement of Gammarus pulex might reduce shredding. However, we have this increase in shredding rate in both species, and we have a flatter decrease in survival in the invasive, which means that increasing temperature is not necessarily going to decrease the rates of resource processing in these environments. And if I can be provocative, I mean, these are the sorts of patterns that we might expect if we were to do the sort of Chris Thomas-inspired assisted translocation to mitigate the fact that some of our native species simply aren't going to be able to cope necessarily with the sort of climate change that they're facing. So I know we've got some time after I finish here. So are biological invasions always a bad thing? Maybe some evidence suggests that they're not. Don't quote me on that, though. Alison would hate me for saying things like that. So just to finish off then, I'd like to acknowledge Danny Kenner, who's a brilliant master's student. He did the work very well, and someone should give him a PhD, and he is actively looking, so if you have anything, do let me know. And Nigel Taylor assisted with some work, and thanks to the University of Leeds. The other thing that I will plug, just because we haven't had much invasive species work in this session, I know there have been other sessions, is that Alison and her research group are running a biosecurity project for researchers who go out into the field. So if you're interested in any more details about that, there's some training and evaluation about how people communicate risk around invasive species floating around as well. And that's where I'll stop. Thanks very much.
Any questions? Yeah.
Yeah, so we didn't look. We only looked at the shredding components of the feeding, and I would imagine that you'd see the standard functional response with the predation, where you get an increase in feeding rates, predation rates, as well as. What I don't know is whether they'd preferentially, whether there'd be diet switching in the invasive. There's some work done by Jamie Dick over at Queen's in Belfast. He's done a lot of work on the predation, but we haven't incorporated that into this model yet. Yeah, it's an interesting point, and I don't know the answer.
Any other questions?
Hmm. That's right. Yeah, so every time you see Dicryogammas going into a system, you lose your native amphipods pretty much overnight. They come in and just mow through anything that's smaller than them. They're voracious. And gammas simply can't cope. So yeah, the first thing that happens is almost complete replacement, which is why we weren't too worried about having treatments where we mixed both species, because that just doesn't happen. So yeah, that's what happens.
Any other questions?
Yeah, that's a really good point. So we're using sycamore actually in this experiment, but we have alder and oak in the lab as well. We're running the experiments using different litter types, and I don't have the results, but Will Fincham, who's been working on the system as well, says that there's no real difference between the species. So we're reasonably sure that this is a robust result across litter types. But yeah, very good point.
Very nice. The invasive Dicryogammas, you found that it had a broad temperature preference.
Yeah.
Could that be just that it's moving more, moves around more? Do you try and get up very good temperature gradient to see what distribution would be?
We did, yeah. So what I haven't shown is the control. So that's in the supplementary information for the paper. And yeah, it's flat for both. There's no preference shown. So the patterns, the activity patterns that we describe in the plot that I showed you are the result of the thermal gradient and not of general activity. Yeah, thanks. Yes, it's up as a preprint on the White Rose repository. So I'll send you a link, or come talk to me and I'll send it to you. Yeah. I can tweet it as well. That's right. I definitely can.